So I have a question here for us to look at. I want to find the surface area of the solid generated by rotating the graph of f of x equals x squared, just kind of a generic parabola, from x equals 0 to 2 around the y-axis. So we get a cup shape, like I've got here in the diagram. Now there's two ways we can approach this, right? Because we've got two formulas. We've got one where we're integrating with respect to x, and another where we're integrating with respect to y. And I'm going to do the same problem twice, once with each of these formulas, because that's really the takeaway that I want you to have here, right? I want you to see that these formulas have nothing to do with the axis that we're rotating around. I can use both of these formulas for the y-axis. I can use both of them for the x-axis. All that matters is the function that we're using to define the curve. Is that defined in terms of x, or is that defined in terms of y? So first, I'm going to use the d of x version to find this surface area. So our f of x here is going to just be x squared, right? It's the original function. So I needed to substitute something in there for that r of x, and remember, it's going to have to be in terms of x, because that's the variable we're integrating with respect to. So if I draw it as kind of a representative slice here, the coordinates of that point, remember, are x comma x squared. So what is the length of that segment? Well, it's just going to be x. Right? It has how far over we have to go on the x-axis to get to that point. Okay, and how about our limits of integration? Well, again, because we're integrating with respect to x, the limits of integration need to be x values. They need to be values from down on the x-axis. All right, so on the x-axis, we go from a equals 0 over to b equals 2. Those are all the things I need to substitute into this formula and get something I can actually integrate. Okay, so this is just a formula, right, just a straight up formula. And I'm going to make all of those substitutions. I'm going to put 0 and 2 in for a and b. I'm going to put x in for r of x. And f prime of x is the derivative of x squared, which is just 2x. Okay, and we can do this. This is actually going to be just a pretty straightforward u substitution. That thing under the square root it's 1 plus 4x squared if we multiply out that exponent. And that's what I'm going to substitute. I'm going to let u equal 1 plus 4x squared, which means du is 8x dx. If I do all my usual u substitution business, this becomes 2 pi integral from 1 to 17. Those are the new bounds in terms of u. Times 1/8 integral of u du. And that's a pretty straightforward integral, right? The 2 pi times 1/8, that's pi over 4. And the integral of the square root of u, power rule, right? That's 2/3 u to the 3 halves. We're going from 1 to 17. And now we can just substitute some numbers. Right? Pi over 4 times 2/3, that's pi over 6. And if we put the 17 in the 1, it's 17 to the 3 halves minus 1 to the 3 halves. 1 to the 3 halves, now we can simplify. 1 to the 3 halves is just 1. So there's my final answer. Not the prettiest thing in the world, but we were able to come up with an exact result. So hold on to that. Right? We're going to do this exact same integral again, this time using the dy formula. And first I want you to see how we reinterpret the problem in terms of that formula, and then, of course, I want you to see that we get the same result both ways. Okay, so let's revisit this. That is my surface area dy formula. And I need to do the same identification, right? I need to come up with the same parts. What is the equation of this curve in terms of y? So if I take my original formula, y equals x squared, solve that for x, I get x is equal to the square root of y, or y to the 1/2. So that's now the function that I'm thinking in terms of. Okay, now we need to do the same thing here with the radius. What is the height, the length of this line in terms of y? Well, remember, in terms of x, it was just x, right? So if we substitute x into our formula here, we get, this is just the height. I hate to say height. If you think of this turned on its side, this is the height in terms of y, which is just our function value. It's y to the 1/2. Okay, and finally, we need some bounds for this integral. Again, we're integrating with respect to y, so I need y-axis values. Well, this first point down here, the y-coordinate is 0, 0, 0. And what is the coordinate of that upper right-hand point there? Well, when x is equal to 2, y is equal to 2 squared. I'm actually going back to the original equation here. So the coordinates of that point are 2, 4, which means 4 is the y value. That's going to be my d. Okay, so we put those into the formula, right? This is just the standard formula here. If I substitute those things in, g of y, remember, is y to the 1/2, which means g prime, power rule, 1 over 2y to the 1/2. So doing all my substitutions, we get this thing. 2 pi integral 0 to 4, y to the 1/2, square root of 1 plus 1 over 2y to the 1/2 squared, dy. Now, I can do some simplifying on that thing inside the square root, right? 2y to the 1/2 squared is just 4y. And now I'm going to keep simplifying here. I'm going to combine these. I'm going to turn the thing under the square root into a single fraction. If I do a common denominator, that's 4y plus 1 over 4y. So you see what's going on in the denominator there? That denominator is the square root of 4y, which is 2 square roots of y. And that square root of y in the denominator is going to cancel with the y to the 1/2 out in front. And then the 2 in the denominator is going to cancel with the 2 in front of the pi. And we're left with this thing. And again, this is just another straightforward substitution. You would let u equal 4y plus 1. Right? And you can work out all the steps if you want to see them. I just kind of jumped right to the final result here. It's pi times 1/4 times 2/3, 4y plus 1 to the 3/2. And I've got it still in terms of y, so we're still going from 0 to 4. Right, so we can do some simplifying. Pi times 1/4 times 2/3 is pi over 6. Now let's do the substitution. If I put 4 in there for y, that becomes 17 to the 3/2. And if I put 0 in there, that becomes 1 to the 3/2, which is just 1. And sure enough, look at that. We came up with exactly the same result. Okay, so big takeaways here. The axis that you're rotating around does not determine which formula you're going to use. The only driver for that decision is, do I have x equals a function of y, or do I have y equals a function of x? And that's it. All right. So coming up, if you'd like to see another example of this kind of thing, we're going to work another one here where the axis of rotation is not one of the coordinate axes, right? Where it's a different horizontal or vertical line. Or you can jump ahead to the next lecture where we're going to start looking at some physics examples, right? Some physics situations that we can, some physics questions that we can answer using our new integration techniques.